Okay, let's take a look at an example from the density altitude worksheet. We start with the fact that we have a single engine aircraft at a mountain airport at an elevation of 6,000 feet. And we have to make some calculations. Now, the first one is rather straightforward, and really no one should have a problem with that. And that's calculating the temperature in Fahrenheit. Now, we know that if we're at 6,000 feet and we've got to correct the pressure to sea level, we did that in a previous chapter, and it says that we've got to adjust by 1 inch of mercury per 1,000 feet of elevation of the airport. So that means that if we divide 6,000 feet by 1,000 feet and multiply that by 1 inch of mercury, we get 6 inches of mercury. So to correct 2392 inches of mercury, which is the airport pressure that we observe here, we add the 6 inches and we get the 2992. That is the airport station pressure corrected to sea level. That means the pressure altitude is 6,000 feet because remember, if there was a difference between the standard temperature pressure, standard temperature is 59 degrees Fahrenheit, standard pressure is 29.92 inches of mercury. If there was a deviation from that, we would add or subtract from 6,000 feet. So what we've got here is we took 2992, we subtracted 2992, we got 0 times 1,000, and so we added 0 to the 6,000 feet elevation to get the airport pressure altitude. Now, next, we're going to attack the rule of thumb density altitude. Well, we've got to calculate the standard temperature at elevation. And that says you've got to decrease standard temperature, 59 degrees Fahrenheit, for each 1,000 feet. So we've got 6 times 1,000 is the number of thousands of feet, times, in this case, we're going to decrease a negative 3.5, so we're going to subtract 21.5 from 59 degrees to get, for our airport, our standard temperature is 38 degrees Fahrenheit. So that's the temperature we have to use in our calculation. So we're going to get a density altitude correction factor by using the formula. The temperature recorded at the airport, which was 68 degrees, minus the standard temperature, which is right here, 38 degrees. We're going to divide by 10 and multiply by 100, or multiply by 600. Or if you divide 600 by 10, you get a factor of 60. So we take our recorded temperature that we converted from Celsius to Fahrenheit, we subtract the correction factor, we multiply that by 60, and we get a rule of thumb correction factor of 1,800 feet. Now, it says use the airport pressure altitude instead of the field elevation. Now in this case, they're one and the same because we had 29.92 as the pressure, so there was no correction. And so we add 1,800 to the pressure altitude, which we calculated to be 6,000, to get 7,800. Now we have to look at, can we clear an obstacle? Now, the key here is that these are not correct entries, so don't go putting these in your spreadsheet because they're not correct. They're only for the purpose of illustration. So the first thing we're going to do is compare the roll distance to the runway length. In other words, does the aircraft have enough runway to take off? So the takeoff roll distance is 1918 and the rate of climb is 300. Again, not correct from the chart, but we're going to use them. So we subtract the total distance given in the worksheet from the roll distance. The obstacle distance in feet from the initial runway position was given as 5 nautical miles. And so if you multiply 5 nautical miles by 6,080 feet per nautical mile, you get 30,400. Again, the actual is 6,076 feet, but for demonstration purposes, we're using 6,080. So we take the distance to the obstacle, we subtract, because we're still on the ground while we're rolling. So after we are airborne, we have 28,482 feet. That's the distance between you and the obstacle. So if you are traveling at 7,800 feet per minute and you've got to go 28,482 feet before you get to the obstacle, how long are you climbing before you get to the obstacle? Well, you divide this number by your forward speed and you get that it will take 3.65151 minutes. Again, this is for illustration purposes only. So if you're climbing at 300 feet per minute, that's what we got for our rate of climb from the table, and you're climbing for 3.6515 minutes, how high will you be? Well, it's your climb rate times the time that you're climbing, and you find out that it is 1,095.46 feet. But the obstacle is at 1,200 feet, and you're only going to be at 1,095.46, so you're not going to clear the obstacle. And that's the whole purpose of this entire collaboration with your colleagues, and that is to understand the impact of what's going on in the atmosphere in terms of temperature and pressure and density to determine what are the characteristics of the flight going to be. So it's much, much better to know you're not going to clear the obstacle before you take off rather than encountering the obstacle after you've already taken off. I hope this brings to light what we're trying to get across in the calculations for this exercise, and we will engage in a discussion of what does this all mean.